In this presentation, we will discuss truth tables and how to realize them using logic gates. A truth table is going to consist of two sides, an input side and an output side. The input side is going to list all the possible combinations of zeros and ones that can occur. And the output is going to be some particular scenario of zeros and ones wanted for that situation. So in binary, we have two states. We can talk about 0 and 1, or true and false, or high and low. And so let's establish a convention that I will use unless explicitly stated otherwise. 0 and false and low will all correspond, and 1 and true and high will all correspond. On the input side of the truth table, it's important that we have all possible combinations. I'm going to express my inputs as zeros and ones, and then I can use a simple counting technique to make sure that I have all my combinations. If I have two inputs, my combinations are 0, 0, 0, 1, 1, 0, and 1, 1, which I can think of as 0, 1, 2, 3, counting. Similarly, for three inputs, my combinations are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1, or I can think of them as the numbers 0 through 7. And in general, if there are n inputs, there will be 2 to the n combinations, and if I want to count, I would count starting from 0 and go up to 2 to the n minus 1. So what we want to do is learn how to express any truth table in terms of Boolean operators. We will use and, or, and not, and then we can have the corresponding logic gates and, or, and not, and then we can build the corresponding circuits. There are different ways to do this. We're going to start with an approach that builds up from the idea that any one line of a truth table can be expressed using ands and nots. Here we are showing 4 different two-input truth tables in which the output has 1, 1, and the rest zeros. So in the first one on the top left, it's the expression for a prime b prime, which is a 1 for the first row and 0 for all other rows. On the upper right, we are writing the expression for a prime b, a inverted and then ANDed with b, and that is a 1 for the second row and 0 otherwise. The third, the lower left, is a b prime, and that is a 1 in the third row and 0 in all others. And the last one is a b, which is a 1 in the fourth row and 0 in the others. Because the expression a prime b prime was 1 for that first row and 0 for all other rows, we can think of it in some sense as the expression for that row, at least in the technique that we're going to follow. Similarly, a prime b is the expression for the second row, a b prime for the third row, and a b for the fourth row. So next we're going to exploit this to have a technique for writing an expression for any truth table, no matter how many 1 outputs there are. So here's our approach. Take the 1 outputs. Just completely ignore the 0 outputs. Take the 1 outputs. Write an expression for those 1 outputs. So write the expression for that row if that row has an output of 1. And then when you have all those expressions, we will OR them, and then that will be a full expression for the full table. So let's consider an example of majority rules. We will have 3 inputs, A, B, and C, and if 2 or more of those inputs are a 1, then we will get a 1 as an output. It's important that you realize that this is just an example, that the input side of the truth table, the A, B, C side, will always be the same. We have all 8 combinations spanning from 0 to 7 if we're using the counting technique. But the output side could change. It won't always be majority rules. We're just considering it to be majority rules for this example. So shown here is a 3-input truth table. A, B, and C are the inputs, and we have all 8 possibilities of 0, 0, 0 to 1, 1, 1. And we've written down the expression for each individual row. The expression would be a 1 for its given row and 0 for all other rows. But in this technique, we go back to the example that the output of the example we're trying to realize, which is the majority rules. And we only are interested in the expressions, the row expressions that were 1. And those are the ones that are highlighted in yellow. So we're going to keep the yellow expressions and ignore the others. So in this approach, you take the rows which have 1s as output, and you write your expression for them, which will involve ands and nots or inversions. For instance, A prime B C. Then we're going to make the overall, so that's an expression for a row. To make the overall expression, we're going to take those expressions that were corresponding to 1s in the outputs, and we're just going to OR them. So our majority rules expression will be A prime B C, or A B prime C, or A B C prime, or A B C. This technique is known as the sum of products. First, we made a product. First, we worked with AND gates, which are like in regular algebra, a product. And then when we had those expressions, we ORed them, and ORing is like a sum in regular algebra. Therefore, this is a sum of products. Make the products and then make a sum of them. So another term for sum of products is minterm. It's important that we don't do any simplifying and that we just keep each term involves all of the inputs. Then that is specifically a minterm expression. If we have the sum of products, it's actually the individual products that are minterms, but we'll still use this term minterm for this approach. So here we're going to build with logic gates this expression for the majority rules. Okay, let's start our focus with the battery. The battery, there's a short end of the battery and a long end of the battery. The short end of the battery is also connected to ground, meaning that that is 0 volts. Then the long end of the battery is 5 volts higher than that. So the lower horizontal line corresponds to a level of 0 volts. The upper horizontal line corresponds to 5 volts. And so we have a low and a high. Next, we have 3 switches labeled A, B, C, and the switches allow us to either connect to the lower wire or to the upper wire. In other words, to be either low or to be high. In the picture shown, the A and the B are connected to the lower wire and thus are in the 0 state, and the C is connected to the upper wire and then is in the high state or true state. At the output of switch A, we have a wire going down from that switch, but peeling off of that wire, we also have an inverter, a NOT gate, that little triangle with the circle on it pointing down. This means that we have access to not only whatever state A is, but if we connect to a wire that is after the NOT gate, we also have access to not A or A prime. And we do a similar thing for B and C inputs. Okay, now let's look at the AND gate sort of going horizontally. The first AND gate is connected to A, B, and not C. The second one going down vertically is connected to A, not B, and C. The third is connected to not A, B, and C. And the fourth one at the bottom is connected to A and B and C. So the AND is giving us our product terms, and we are getting all the combinations in our expression for majority rules. And then our final step is to OR those. So we send all those, the outputs of the 4 AND gates are all piped into a 4-input OR gate. And then the output of the OR is our overall output, in which we put a probe. And the probe will when the circuit is functioning, light up if the output is true or high, and remain sort of not lit up if it is false or low. So in this picture here, we have not changed any of the wiring. We've only changed the values of the switches. So now we can see that A is connected high, B is connected low, and C is connected high. So two of the inputs are high. And again, we were realizing majority rule. So 2 high should give us a high. And we see that the probe of the output over there on the right is filled in, is lit, is high, is true. So again, it's important that you understand that majority rules with just an example. And so now we will do another example, a different example. The input side, the A, B, C, is the same as it was before. It's just all the combinations of the inputs. We're working with zeros and ones and taking the sort of counting approach. So we count from 0 to 7. Therefore, we have all 8 possibilities. And then the output is different in this scenario. And whatever it happens to be going down from the top row to the bottom row, 1, 0, 1, 0, 0, 1, 0, 1. And we're going to focus on this approach. We focus on the ones, so we pick out with the blue arrows the ones. We will ignore the zeros and focus on the ones. And then we will write the expression for those ones. So the top expression is A prime, B prime, C prime. And you can see that we're focusing on ones, and then we write the expression that sort of forces that row to be a 1. So if A is 0, B is 0, and C is 0, and we want a 1, then we invert A and invert B and invert C so that we get all ones. The next one down that we're considering, the next blue arrow, is A prime, B, C prime. So the zeros get primed and the ones do not. And then the third blue arrow going down is A, B prime, C, and the last one is A, B, C. And we take these AND expressions and then put ORs between them. So again, this is the sum of products. You start with ANDs with some maybe nots, so this is a product, and then you have a sum of them, you OR them. And this is made up of minterms, so it's also known as a minterm expression. Next, I want to show you that you can always take this approach, though it might not always be the best approach. So let's imagine the following example, where the truth table has a 0 for that first row. So A, B, C, all zeros gives a 0, and all other rows give 1. So now we have 7 terms to write. So we can pursue our sum of product approach. We can write our 7 products, as you see there, and we can sum them, really ORs. But this was just the truth table for a 3-input OR. You remember that an OR, if all the inputs were false, it gave a false, or if all the inputs were low, it gave a low. So that previous truth table was the truth table of an OR. So this, as all truth tables though, there is more than one way to express them. So now, motivated by this example, we're going to learn another technique. And in this technique, we will be focusing on the zeros of the output. So in this alternate approach where we focus on outputs which are zeros, we're going to write expressions that are ones for all the lines except for the line of interest, which is then going to be a 0 for that line. And this is going to be an OR. Remember, that's how ORs work. And then we will, in our terminology, refer to it as a sum, remembering that sort of OR and sums are somewhat similar. Then when we're all done, we are going to AND the expression. So we're going to have what we call a product of sums when we are done. Shown here are the expressions for each row. Remember that we are going to write an expression when the output is a 0, and we want an expression which is 0 for that row and 1 for all others. So our first row is A or B or C. That would give me a 0 if A is 0 and B is 0 and C is 0, and it would give me a 1 for all other possible inputs. And so we are making our inputs 0. And so for the next row, it will be A plus B plus C prime. Then it would be 0 or 0 or 0 after the C is primed, and so on. So to emphasize that we could take either approach, sum of products or product of sums, to any of our truth tables, we return to a previous example. And now we're going to take the product of sum approach. So we will focus on the 0 outputs and write their expressions. So that expression for the first blue arrowed row is A plus B plus C prime. We are trying to make zeros. So when we see ones, that's when we're going to prime. So the second blue arrow down is A plus B prime plus C prime. The third arrow down is A prime plus BC. And the fourth blue arrow going down is A prime plus B prime plus C. I've put these expressions in parentheses because our next step is going to be multiplying them. And again, like regular algebra, we have to worry about precedence. And so if we want a sum done before a product, we need parentheses around it to force that to happen. So our final step is to take a product of these sums, and again we want to perform the sums first, so to respect our precedence, our order of operations, those sums are in parentheses and then they are multiplied. So the individual terms are ORed or sums, and then there's a product of them, and this approach is, in addition to be called product of sums, is also known as the maxterm approach. If we are going to build this using gates, the top portion is the same, that there's a battery and that there are switches connected to the battery. So there's an establishment of a low state and a high state, and then connected to the three switches, the ABC switches, are not only a line that comes straight out of the output, but also a line that goes over to a NOT gate and inverts that output, so we have access to both A and A prime. The difference, so that part was the same. The difference is now that we have ORs before we have an AND. Previously it was the ANDs came first and then the OR, but now we have switched that order and the ORs come first and then the AND. So that first OR gate at the top is A or B or C prime, and going down it's A or B prime or C prime, etc. And then those four OR gates are finally ANDed, and then that final product, that AND gate, is sent over to a probe to indicate the overall state of the output, whether it is high or low, whether it is lit or not. So if I have all of my inputs, maybe primed, maybe not primed, ORed together, that's known as a maxterm. And this approach then uses maxterms, or is the maxterm approach. So here we're just sort of summarizing in one slide the expressions used by either approach. The minterm expression uses an AND, and the maxterm expression uses an OR. The minterm expression is trying to create a 1, and so if you see a 0, it's going to be primed. Whereas the maxterm expression is trying to make a 0, and it is going to be primed when there is a 1. So let's look at row 2. We see it is A is 0, B is 0, and C is 1. When we're trying to make a 1, we change the A and the B, so it's A prime, B prime, C. But in the maxterm approach, where we're trying to make a 0, it's the 1 we don't like, and so it's A plus B plus C prime. And here I'm just showing some of the references I used to put together this talk.